packages. So once you have installed these packages, let's import all the packages that we need for our. So these are the necessary packages. And mglearn is the library that actually helps you create a data for this. Say for example, if you give you a data set of this form, say all the circles are of one type. So circles belongs to some class 0 and the triangles belongs to class 1. So mglearn helps you create such fake data set where you can actually perform some testing and your algorithm testing. So this is the case. So you have some data points class 0 and the triangle as class 1. And there are only two features if you see. So we have created two features, the first feature and second feature. So x belongs to feature 1 and feature 2. And there are two classes, which is class 0, 2, 1, and triangle as class 1. So what I meant by two feature is that x has only two feature, two dimensions there. Each data point is represented by two feature points, feature 1 and feature 2, and each point belongs to either a class 0 or class 1. So in our temporary data set that we have created is of 26, 2 size. Now let's actually start building trees now. So for example, let's import this another package which will help you in visualizing things, uh, how trees are constructed. So we will construct a decision tree. The first thing we will do is construct a decision tree. So for example, consider this is the data point. You have uh, class 0, blue dots, and triangle of class 1. So these are the data points. And you can clearly see that a spiral-like structure would be a better decision boundary. A spiral-like thing will be able to divide the class 0 and class 1, much more perfectly. But let's use decision tree to make our classification. Let's see how it does. So in depth 1, the first thing that you can do is actually just draw a straight line to judge whether this belongs to class 0 or class 1, class 0, blue dots, or class 1, the triangle. I think this straight line is the best straight line that actually makes the majority of the data points as pure as possible, right? So you can see that if x is x1, the feature 1, this is feature 0, and this is feature 1. If feature 1 is less than or equal to 0.06, then you say, if it is less than this, then you can say these are all class 1, else it is class 0, if you have a depth of 1. But let's increase the depth. As we have discussed before, as we increase the depth, our accuracy also increases, but we end up overfitting to the noise too. So as you can see that these small triangles that have ended up being here, these are small noise that is there. So for example, this blue circle that is over here and the triangle over here are noisy system. So if you try to fit, if you increase the depth very large, it may end up start to overfit. So let's see how depth 2 looks like. So now depth 2 is that, okay, once we have the straight line, means we have divided the data set. Now in this region, if x0 is less than minus 4.18, which is x0 is less than minus 4.18, then you say it's a class 0. And if it is greater, you simply classify as class 1. As you can see, now majority of the data points have become more pure by choosing a straight line x1 classification. And similarly, the other side, when in class 0's data point, if you actually set class x0 is less than 1.16, it becomes, if this line is there, then these are all class 0 point, and above that is all class 1 point. Now you can see that it's somehow kind of a spiral shape. See, this left angle, and this is the blue angle. We are able to somehow build this spiral shape just by depth 2, right? Now let's increase the depth. Let's actually even classify these data points, even though there is only one noisy point. We will try to classify, make it as accurate as possible, and these data points that are there. So if you see what happens at depth 9 is that as you continue to increase the depth, you start actually even distinguishing that you draw a straight line over here just to make sure that this triangle is also correctly classified. Draw a straight line such that this circle, the class 1 data point that is over here, is also correctly classified. So you see the depth 9 has now overfit the data set, and the accuracy on the training data point is 1 now. You see, this is not a good classification, right? Even a naive person can tell you that this is not a good classification, as you have now started to overfit the data points, and class level 2 is sufficiently a good classification model, right? You can consider these triangles, small number of triangles that are misclassified, are some noisy behavior, and level depth 2 will give you a very good accuracy compared to a depth 9, because now it has started to overfit the data points now. Makes sense? As we have discussed before, in decision trees, as you increase the depth size, you will get an accuracy of 1. You will approach an accuracy of 1. However, you will end up overfitting to the noise of the system. Okay, I will wait for a minute to see if anyone has doubt regarding this part, that how in decision tree, if we increase the size of the tree, we are able to achieve accuracy very close to 100% or 1, but it is actually overfitting to the noise in the data, which is not a good classification model. A lower depth is a good classification model. In this case, level 2 or level 3 might be a good classification model. Also the point, let me just wait for a few. Okay, if there is no further doubt. So now the other point that I also wanted you to know is that look at this feature, like x1 less than 0.016 is a very important feature, as this line is able to maximally separate all the data points, like make all the separated data points of same or homogeneous or pure. So all the data points that are below this line are more or less all triangles, right? And all the data points that are above this blue line are more or less class 0, right? So this line, the separating line, is a very important feature in our uh, classification model. So this becomes a very important feature. And the second most important feature is this line that you have drawn based on feature 0. So this line is based on the feature 1. Feature 1 seems to be a more important feature. And then this line, the second line that you have drawn, is a feature zeroth feature. Now, as you progress, you have started to add more and more complicated feature lines. But these feature lines are not so important. They are now fitting to some noise in the data points. So one needs to be careful at what depth you need to stop. Okay, so this is a toy example that we did. Now let's look into some real world example. Now we will actually be looking at the breast cancer detection task. So we'll first download all the data points and see what all data points are there. So we will see what all data points are there. So there are 569 data points, with each data having 30 different features. Okay, so we will see what all different features are there. But assume there are 30 different features for a given person. So there are 569 people's data, and each person has 30 different features in it. So 30 different tests have been performed. So let's see. So in this case, how many data points? So there are total cancerous patients. There are 212 people with cancer, and benign is there are 357 benign patients, no cancer patients. Now let's look into all the 30 features that are there. So if you see 30 features, there is this feature number one is the median radius. Maybe the median radius of the cancer itself, maybe I don't know. But this is these are some of the features that are there: mean parameter, mean area, mean smoothness, mean compactness, mean convexity, fractal dimensional error, worst parameter, area, worst texture, and worst fractional dimension. So these are 30 different features that have been identified. So someone has given you these 30 different features of a given of a single patient. So you can see that there are total of 30 features. So if you just look at the length, how many features are there in the feature name? There are 30. So each person will contain all 30 features that are there. And now your goal is to identify if a given person has a cancer or not. Okay. So first to do that, we will first split the data set into training data set and the test data set. So we will consider 30% of the data as a training a test data set. So out of 569 data points, we'll choose 30% of the data point as test data point and the remaining as train data point. So let's look at the what is the number of data points that we are looking at. So X train, let's see. So X now the training data point has 398 data points are training, and the test data set has around 171 as test data points. Now notice, recall that on the test data set, we never train our model. Test data set is used to report how good your model is, right? You never train on the test data set, you only train on the train data set. So now let's look into how does this look. Now let's create a decision classifier, decision tree classifier. It is already available in the SKLN tree package. We'll set the random state to 0. Okay. So now in this case, since you have not set the maximum depth of the tree, it will construct a tree which is of full depth, like until the entire data becomes pure. Until unless the entire data becomes pure, it will continue classifying. Remember this one? It continues to create the data and it continues to classify until all the data points become pure. So it reached a depth of 9. Similarly, if you want to create a full tree without any restriction, you just use a max. There is no maximum depth. Don't set maximum depth. So let's look into what is the accuracy. The accuracy of the training set is 1. As we have discussed before, if you let your model completely let this, you do not control the size of the tree, it will eventually reach the accuracy of 1. As we can see, the accuracy of the on the training set is 1. But on the test set, it only is able to reach 91% accuracy. So 91% is not bad, but it may have overfit some of the data points, but we can do better than 91. So let's see what happens if we restrict the maximum depth to 4. So if we just restrict the maximum depth to 4 and train our classifier entirely the same way, so we see that the training accuracy has reduced. It is now no longer as 1. It has become 99.2. However, the test accuracy have increased to 92.4, right? So if you increase the max depth to say 5, if you increase the depth to 5 and you see the accuracy did not change much. Let's say I make it 9 and you see the accuracy have reached 1 and the test accuracy has reached 1.1. It became same. See, the maximum depth is 9, meaning that by ninth depth, it is able to expand the tree fully, and there is no data point that is remained unclassified. So if you set the maximum depth to 7 and see what happens there, so you see even at level 7, it has already classified full data set. So level 7 is also fully expanded. So level 6 is also fully expanded, and level 5 Level 5 is the one that was not fully expanded. The sixth level was the fully expanded level. So level 6 in the previously in this demo example, we had depth 9 as fully expanded. Even if we said depth 10, depth 9 has fully expanded the data set. So depth 10 it will never reach there because all the data points have become already pure. So maximum depth of 9 is the full expansion. So even if you set maximum depth to 12 or 7, 12 or 20, the tree will be only be constructed of depth of 9 because after that there is nothing to classify for. Similarly, in this case, the maximum depth in this decision tree is 6. So anything above 6 is always constructing a tree of size 6. But if you construct a maximum depth of 4, you are able to make sure that training accuracy is not able to reach 1, but your test accuracy is increased simply because you are now no longer fitting to the noise in the system. So if you make your data point to maximum depth of 2, you can see that the accuracy is 95% and you are still able to maintain the test accuracy equal to the previous one. Just with depth size 2, you're still able to maintain the same test accuracy as you were making, as you were, uh, as you were able to achieve with the full tree size. See, so restricting the depth size also controls your fitting to the noise system. So you don't want to fit to the noise in the data point. Okay, so now let's analyze this tree a bit. So we will first see this tree 0, which is full tree. Okay, so let's construct the complete tree without any restriction. So you see, you have constructed this big tree of level 6. So first you will start with the worst radius. If the worst radius is less than 16.79 and the value is between 148.0 to 250, you go here. No, the value is something else. If the worst radius is less than this value, you come to, if it is true, you come here. And if the worst, and if you only want to stop at this level, then you will assign the class as benign class, that there is no cancer here. And if the worst radius is greater than this value, then you will say that it is a cancerous patient if you just stop at depth level of 1, right? You can already see that there are only 23 data. So if you just stop at this level, you will see that this is where it will stop. But if you go further, you can actually even make it more accurate by assigning. If you say the worst concave point, if it is less than this value, you will assign it as benign. If you stop at this level, and if it is not, you will assign it as cancerous. Similarly, if you want to continue further, you can actually make use of texture error. If it is less than this value, it becomes benign. If it is not, it becomes uh, cancerous. So even at this level point, if you want to make it more accurate, you can continue classifying further. See? Okay. So before I go further, so let me just let you know what this value thing denotes. Value denotes that what is the total number of data points that are classified as cancerous. This is one. Okay, sorry. Just understand this thing. What is the total number of data points that are assigned as cancerous? There are 148 data points that are cancerous and 250 data points that are non-cancerous. So if you just choose the worst radius less than 16.79, 250 total number of patients are non-cancerous and 148 are people with cancer. So since the majority are non-cancerous, you assign a class of non-cancerous. So if you restrict at the level 0, like your tree size is size 0. So you can construct a tree size of size 0 by restricting the size to 0, I think, or size 1. Oh, sorry. It's the size 1. If you construct a tree of size 1, So you are able to see this much accuracy. So the size, I think size 1 is this level. It's not size 0. Maximum depth is size 1 is this level. It's not this value. So, but the point is that if you stop at just this value, if the worst radius is less than 16, then you assign all the points that belongs to less than 16 as benign class, and if it is greater, then you assign all the 148 data points to cancerous class. So you can see this 148 data points are here. Now, as you go further, you can start assigning class that out of this one, whichever values that are less than 16, less than 16, you can, if you divide the number of total points with this value, so it will reach all benign value here. Whichever is 244 points will go here, and 23 points will go here. Similarly, if you look at the lowest class, you see it has zero benign classes, which means there are no non-cancerous patient. Here there are only non-cancerous patient. Here there are only cancer patient, one. So at the leaf level, the data has become completely pure. There is no error at the leaf level. So all the leaf points you see, there is 1 0, 0 1, 18 0, 0 3, 2 0, and there is 0 3. So all these leaf nodes have become completely pure. That's why you are able to see an accuracy of 1, because now you are able to completely overfit the data points. And you can see that this is not the correct way of classifying, because some of the data points have only one data in it. And this is not the way you should be, you should not have been doing this, because these data points can simply be a noise in the data. So you don't want to fit to the noise in the system. However, let's construct a tree of size 2 to see. Let's construct a tree of size 2 and see how it has been classified. So this is it. So you have worst radius, concave points, and this other tree. So one is 0, 1, 2. So this is all these are. So you can see that there are 3 data points that are there, which are how do I say it? Which are uh, non-cancerous, but 125 of them are cancerous. So you assign it as cancerous. There are 3 that are non-cancerous and 0 of them are cancerous. So you assign them non-cancerous. And similarly, 19 are cancerous and 7 are non-cancerous. You assign it as cancerous because the majority is there. Similarly, in this, 237 are non-cancerous. Simply you will assign them non-cancerous, even though there are. So you can see that this is much better because now you are not fitting to this for a noise in the system, which is like this 4.73. You're not fitting to these data points now. You are now able to make it more accurate. Okay. So I will wait here for a while to see if everyone is able to follow that how restricting the depth size is able to improve your test accuracy simply by not overfitting to the noise in the system. Okay, so I'm assuming there are no doubts. Just check once. Okay, so there are no doubts in chat too. Okay, so now let's look into, as we have discussed before, that decision tree also helps you identify important features. Can someone tell me by looking at this tree, what are the important features? No, what are the important features in the data set for predicting whether a person has a cancer or not? If I just give you this decision tree, what are the important features? Can someone answer? Can someone guess? Let me just print what are the features there. So the features were cancer feature names. Just see all the features name. So these were the feature name. There is this worst radius, worst texture, worst parameters, mean texture, mean radius. So I get. So what are the important features? If you just look at the tree. Okay. So the most important features are these features. The worst radius are considered as important feature as because this worst radius less than this value, some value, is able to it helps you classify the data such that the majority of the data, most of the data in the classified data set becomes pure. So as you classify with it, around 267 data points have become pure, around 244 data points have become pure of same class as no cancer. And at the same, on the other side, 125 data points have become pure with cancerous data points. So worst radius is a very important feature because it is able to help it is able to help you in making the two data sets pure, maximally pure. Though there are 23 data points that are those are cancer, and 6 data points here that are non-cancer, but most of the data points here are pure. Similarly, the second most important is the worst cancer convex point because it is able to classify around 241 data points with 237 as non-cancerous and 19 as cancerous. Similarly, here texture error is a third important point because it is also able to help you classify make the data set pure with 125 as cancerous and here 3 as non-cancerous. So these are the top three features: worst radius, worst concave points, and texture error. And that's what you also see here. So if you just plot this value, feature important, you will see that these 3 points that you see here, 0.81, 1479 and 0.034 are the important features. And if you just plot them, you see the worst radius, concave points, and texture error as important importance, right? So 80% of the importance comes from just from the worst radius itself. You see, and the worst concave points is the second most, and the texture error. Third. So since it is a decision tree of size 2, if you increase the size of the tree, say if we increase the size of the tree to say 3, now if we just plot all the data points again, so now it has become the texture, smoothness error, worst texture, worst concavity have started to show up now. So these are all becoming now other features that are important. If you just plot what all things are, even in that case, worst radius is a very important feature. Worst concavity is the second most. Third most is maybe probably worst texture and texture error. Both are the same thing. And worst concavity came the last, like, fifth, fourth most important feature, and fifth most important feature, right? So similarly, if you increase your tree size, you can actually see which are more important, which are not so important. But burst radius is very important feature in helping you classify your data. Okay, so this is how you can use decision tree for deciding which features are important. And you can see this is area error, compactness error, concavity error has almost zero role to play in your classification. So even if these features are available to you, but this is not contributing in any classification. Then you can also drop these features too. Okay, so let's draw the confusion matrix of this. So confusion matrix means if the true label is 0 and how many of them you have predicted also 0. So if true label is 0 and you have also predicted 0 is 56 data points. The true label was 0 and you have also predicted 0. And similarly, if the true label was 0 and you predicted as 1, meaning it has cancer, which is about 8 people are there. Okay. And similarly, if the true label was 1 and you have predicted 0, which is 5. So 5 and 8 are the misclassification because the true label was 0 but you ended up predicting as 1. So this is misclassification. Similarly, if the true label was 1 and you ended up predicting as 0, this is also misclassification of 5. Similarly, when the true label was 1 and you have actually predicted as 1 is 1 not 2. So the 56 and 102 are your classification points. So this is with level 3, I guess, because the tree size I updated it to 3, right? Maximum depth of 3. So tree was constructed at maximum level 3, and this is what you have. Okay. So notice that the test accuracy of the depth of the size at depth 3 is 92.4%. So you were able to achieve a 92.4% test accuracy with a train accuracy of 98.0. So now let's look into random forest. As we have discussed before, random forest is a much stronger classifier. Random forest constructs a forest, meaning you have multiple trees that you construct. Not just 1, 2, 3 trees, you construct multiple trees. There. Okay, let's first look into this data with a small data point. So let's make moons. So you will see what moon data points is does. It has say 100 samples. You are going to create 100 such samples and with a noise of 20.25, meaning that you have added noise in the data point. Some noise you want to add in the data point. So we construct a train test split. We constructed a test split of 30%. So 30 of the data points are test data. Now we have number of estimators. Number of estimators meaning 5 means that there are only 5 forests, 5 trees in the forest. Okay, so you can increase the number of estimators, but currently we are only using 5 trees there, and we are considering all the features. We are considering all the features to construct this 5 trees. So let's construct the trees. Okay, so you will see. So tree 0 is constructing with feature 0 and feature 1. This is what the tree 0 constructed. Like completely it constructed this tree. Tree 1 constructed this tree. Right? Tree 2 constructed this tree. Now tree 3 constructed this tree and tree 4 constructed this tree. Remember there were only 5 trees. Number of estimators 5. So you have tree 0, 1, tree 2, tree 3 and tree 4. And the random forest, okay. So now what you have to do is that you will, whenever a new data point comes in, you pass through all the trees and you choose that the answer is the majority, what the majority says. If the majority says that it is class 0, you just say if the answer is class 0. If the majority says that it is class 1, you say class 1. So if you choose the majority voting and you construct the random forest, and this is how the random forest looks like. Look at this classification. Isn't it much more cleaner? That you see this nice U shape here and nice U shape here with some small error here, but still it is much better than all the trees that you have constructed. All the trees that you have constructed are more or less they have some error in it. They are all overfit the data point, but some error is still there. But if you use the majority voting among those, the random forest is able to get the best out of all the trees. So a single tree may have some overfit to the noise, but if you use the majority voting of such a tree, you will get the best classification that you can. Okay. Now let's go back to our cancer data points. So we have the same cancer data points. So we split. Now here we have constructed 100 trees, not just 5 trees, but say 100 trees we construct. Now look at the accuracy. The training accuracy is 1. Now the test accuracy is also 97%. Did you see? Now with a single tree, you were always able to, if you, okay, let's just construct a single tree. Number of estimator 1 meaning there is only one tree, and if you construct that tree, you get a training accuracy of 96 and the test accuracy of 88, right? So it has just constructed some random tree, and this is what you are able to get. But if you construct multiple such trees there, you can actually construct a full accuracy with a very high test score. You see? Now you are able to draw more important. Now, if you look at what all important features are according to random forest, you see the worst. Just a sec. Last time we saw worst area as the most important, worst radius as the most important. Let's see what is the here. Worst radius is important, but actually worst parameter is even more important, which our decision tree was not able to identify. And now all the other features have started to see some importance there. But still, worst parameter is the most important. Then worst concave point that was also identified by decision tree. Worst radius was also identified by decision tree. So these two were all was also important. And what was the other point that was identified by decision tree? Texture error and worst concavity, concave point, worst texture. Okay, worst texture and texture error. Worst texture, yeah, it is important, but not so important compared to worst concavity, worst area. Mean concave points were also important here. So with random forest, you are also able to find the fine grained importance of the feature too, which you are not able to identify with a single decision tree. But if you construct a forest, you will be able to get more importance out of your data point. And if you construct your confusion matrix, so now if the true label is 0, the prediction is 0, which is 52. The true label is 0 and you have predicted 1. There is only one data points now. Remember there were 8 data points before. Now you with a random forest, there is only one data point. And similarly, when the true label is 1 and you have predicted 0, the error is 3. But if the true label is 1 and you have predicted 1 is 87. Now you have improved much better. Okay. So the idea, the final concluding remark that whenever there is a classification task and if you are given some classification task, the first go-to algorithm should be some tree-based algorithm, maybe a random forest or a XGBoost or ADA boost. These are all random forest type algorithms, but the random forest should be the first go-to algorithm and check whether how random forest performs on your data on your uh, classification task. Because random forest more or less will most likely will solve most of your problem. If random forest doesn't solve, then go for more advanced algorithms. But the first thing that you should try with random forest or any other decision tree based algorithm. Okay, so I will stop here for a while to check if there are any doubts in this random forest algorithm, anything that is not clear. Do you want me to repeat? I wonder why class has become so silent. I'm not able to. Am I not audible? Am I going too fast? I thought that this class would be more discussion. because these are very important class of algorithms, and I hope that in your own application that you will do, you will use these algorithms. If you have any doubt, if you are not able to understand, not able to follow, please ask me. Is there anything that you want to repeat? Okay. If there are no further doubts, then I will share this slide. So this is the tutorial for today. So we have completed decision tree. We saw how decision tree is able to select feature importance. Similarly, we also saw how random forests are constructed, how trees are constructed in the random tree forest, and we choose a majority voting among the trees to construct the final decision boundary. And then we saw that random forest is able to better identify the feature importance compared to the decision tree. And we saw that the random forest has much better accuracy than the simple decision tree algorithm. Okay, thank you again. So let me just share the tutorial with you once. Give me a few minutes. So can someone confirm if they are able to view decision tree? No. Is the tutorial link visible? I have just shared. Okay. Thank you again. Uh, is there any doubt regarding decision tree from yesterday's lecture or today's uh, tutorial? Okay. Thank you again. So please go through these slides and tutorial material. Decision tree is a very important class of algorithm that it should be your go-to algorithm in first go-to algorithm in classification class. Okay. Thank you again. So we can end the lecture if there are no further doubts. Uh, thank you again. So we can end the lecture today. See you in the next lecture.